I never put it into a form where I can properly communicate it, and being allowed to talk here kind of forced me to do so. So this is good. Also, it's really basic idea. It's not applied, but it's clear how it can be applied to HPSS. And it's so basic that I'm a bit afraid that someone else must have done it. And I looked, I didn't find it. So if you're aware of this, please let me know and save me the embarrassment of getting it out into the world. So here is the title, Time-Aware Large Language Models Towards a Novel Architecture for Historical Analysis. It's a bit cryptic, but I hope it'll become clear what I mean by that. So let's start from the observation that currently large language models only have an implicit understanding of time, and they derive this statistically from the text they see in their training. This is not meant to say that they don't understand time. They understand an amazing lot about time, but again, they take this from the implicit cues that they find in the training data. Now, explicit time awareness, and define what I mean by this in a minute, would certainly, and I think this is almost a no-brainer, benefit their application in historical analysis, but also, I'd claim, beyond. And what do I mean by this? Let's look at the concrete examples, given this sentence, which or these two sentences, which are different only in their last two words. They're really contradictory in a sense. We don't even see the contradiction because, by default, we kind of know that these two sentences are uttered at a different time. So the first completion represents the state of affairs in 2017, and maybe the second something like today or more recently. Now, however, when these two sentences are in the training of a large language model, we don't give it this information. They really compete against each other. And for attention in the true sense of the word. And the model has to decide which one to give preference. And it cannot fulfill its objective perfectly because it decides for either one and it'll make at least one mistake because it doesn't get the other one right. And then we train the model, and then once we have the trained model, we use it for next token prediction, and we give it this input token sequence again. And we ask it for the next token, and probably it's gonna give us transformer. It's been mentioned yesterday. There's a recency bias. We can discuss why the models develop this in the discussion. And of course, somehow it has seen the long short-term memories in its training. It's somehow in there. There's no way to get this out other than to change the context. To change the token sequence on which the generation of this next token is conditioned. You may put in 2017, you may change the tense of the verb, and then if you do a next token prediction, maybe and hopefully long short-term memories comes out, but there's little guarantee for that. It's basically prompt engineering. It's a bit fishing in the dark how the model has learned to understand time, and you try to exploit this. And there's certainly scenarios in which you want to do better, and you want those models to be explicitly time aware, and should have become clear by now what I mean by this, like be able to learn and reproduce the changing patterns in their training data as a function, explicitly as a function of time. I think I found a way to do that. It's a very trivial way, actually. And I will present this today to you, and it will also give you the proof of concept based on a small, and I just added this yesterday, generative large language models. So I'm talking about large language models that actually produce or reproduce the text, the patterns they've seen in the input data. So let's formalize what I just said a bit further. You all know what those large language models do. Based on their training data, they estimate the probability distribution over the vocabulary for the next token given a sequence of previous tokens. So given this token sequence that they have here, they will provide some or learn some estimate of the continuation LSTM, so the continuation transformers and then spit out the one that is most probable. This is how they function, basically. Of course, we know that in the real world, the probability of a token given its preceding context is not static, but it depends on time. It's really a function of time. Now, take the example. In 2017, the probability that transformers is the completion of that sentence was 0, simply. And then if you have the probability for the next token, you can, of course, you get the probability for the whole token sequence. And again, we know that the probability distributions for those token sequences are, in our training data are dependent on time and not static, but they're treated basically as static in the training process. And as a consequence, during inference, the large language model can reflect a temporal drift in this distribution, but only via in-context learning. And that example we saw on the last slide. Now, again, if we want to improve on this, what do we have to do? Well, somehow we have to model this time-dependent probability distribution. How could we do it? Well, I've seen approaches where you do time slicing. So you train a model for certain slices of time where you kind of, for those slices, assume that the distribution is more or less static, and then you could use the model for that time slice that you're interested in. This is, of course, extremely data inefficient. So here then comes my idea, and it couldn't resist temptation to call it the time transformer. And the idea is really, really simple. As you know, and we've heard several times over, every NLP task starts with transferring the words, the tokens, into some vectorial representation, an embedding. And that's the same in language model, in transformers. So you have an embedding into this latent vectorial space, and that embedding is not predefined. It's learned during the training. And the idea here is simple. Just add one additional dimension that codes for the time of that token. So every sequence that goes in there was uttered at a certain time. Just give it explicitly the time. So every word there, dog or get Krasov, can slightly be different in that one dimension, whether it was uttered today or like 5 years ago or 10 years ago. And then simply, if you do this, what you give into the transformer is a sequence of these tokens embeddings. Now, they are all dependent on time, meaning if you send them through the transformer, you will get the time-dependent probability distributions, right? And the training objective with these remains the same. We maximize the log likelihood over all sequences and partial sequences, or minimize the negative of this. And then maybe in a bit more natural language, so we inject time into every token's representation. And then the beauty of it is that the model can learn exactly how strongly or weakly that time dimension in the end influences each token. I mean, for certain words, probably doesn't matter much. For others, it matters much more. And it's the transformer architecture that really will process this statistical information in an efficient way. So that was the idea. I needed to test it. Of course, very difficult to train a generative large language model. So here my idea was, is there some data set where you have a very restricted language, small vocabulary, repeating language patterns, so where the patterns are not very complicated? And I came up with the idea to use weather reports. And I found that the UK's National Meteorological Service puts them online, has past reports accessible. By the way, when preparing for this, I find that there's another interesting data set that I could have used. It's called Tiny Stories. I just listed it here in case someone wants to use that. So this is how it looks. You get them as PDFs for each month of a year, and then you have one weather report for every day. I scraped this for the years 2018 to 2024. Gives me 2,500 reports of that length approximately. And then we chunk it, we tokenize it. You can see very simple, no subword tokenization, neglect case, neglect interpretation. It turns out they're really simple. They only have 3,400 words in these like 7 years. And then I had to train a model to see if I could learn the patterns, the language patterns in that data set. So I built a very modest transformer model. I assume you have a general idea of the work. We had this discussion yesterday about LLM literacy. Maybe not, but it's very simple. So every token gets its representation, and it goes through the transformer, through various decoder layers, and every decoder layer, the representation of each token picks up on the context, and then really you get an enriched representation, and then this is used for like this massive classification task to assign it to like each a probability to each token in the vocabulary. A bit more detailed, you have it here. Mine has 4 decoder layers. Each decoder layer is made of one multi-head attention of 8 heads, and then you have the norm, then you have a non-linear layer, and the norm again for decoder layers, and then this final dense layer that's responsible for the assignment of the probabilities. This is very small. It only has 39 million parameters, 150 MB. Compare this to GPT-4. And I trained it on our HPC cluster in Munich on 2 H100s, and it only takes 11 seconds per epoch. This is because the data set is super small and the model is super small. So you can train it on this as well. And the code I've made available, don't use it. I did produce this code because I wanted to implement a transformer from scratch to understand it better, so they're better implementations. So if you want to do it. And it's also the code for the experiments that I'm going to show. So I train it, and then I have it generate weather forecasts, as it were. So you give it a seed sequence during the night, a band, and then you have it auto-regressively generate token by token until you have a weather forecast, and we can add in like interpunctation and capitalization. Again, if you read it, you will not be able to tell it apart from the actual weather report. So you could say, yeah, it has picked up on the pattern that it has found in the training data. Nice. So we have a small language model for that restricted toy case. And now, how do we get to the time transformer? And here's the beauty of it. The adjustment to the architecture is so super minimal. So instead of embedding everything in my case, a 512-dimensional latent semantic space that is built up during training, reserve 1 dimension for the time. That's it. So to tell every token, like this sequence was uttered at that date, and then give it in. In my case, how do I do it? I make it non-trainable, min-max normalized day of the year. Why the day of the year, you'll see in a second. There are, of course, seasonal variations that I wanted to exploit that are in that data naturally. So you have snow in the winter, it's hot in the summer, so that made sense. But of course, you can have every other time embedding that you want. So now the question is, can this new structure efficiently learn temporal drift in the underlying distribution? And my first experiment was to just inject a temporal drift in the training data by a time-dependent replacement, where I replaced rain by liquid sunshine, dependent on the day of the year. It's just simply a sigmoid function. So in the beginning of the year, you don't replace it. In the end of the year, the probability for replacement is 1. So there'll always be liquid sunshine at the end of the year and something else in between. And then to test this, I generated like 1 weather prediction for each day of the year and just counted for each month the frequencies of rain versus liquid sunshine in these months. And you see it perfectly reproduces the pattern that we put in there with some statistical variations that you would expect. But there's only rain in the beginning, almost only liquid sunshine in the end, and the switchover is exactly in the middle of the year. So it's picked up this pattern. And then, as I said, yeah, oh, it's nice. I already have like naturally occurring temporal patterns in my weather forecast. And I looked at them, and they're there, but in a sense, they're just more of the same. You know, it's like you have one word, and it's more frequent or less frequent, depending on the time of the year. So I thought I needed a bit more complicated case. And here the idea, and it's a secondary experiment, was to inject again some synthetic time drift, where I wanted to change a co-occurrence. And the trick is here not to introduce something absolutely new in this language. So it had to somehow respect the language patterns that were already there. What I did here is I looked for occurrences of rain, not followed by and when that happened, I replaced it by rain and snow. So in a sense, you could say I changed the weather. Of course, from the perspective of the model, I just changed the language. So in linguistics, this would be a collocation, fixation of collocation, so like in bread and butter. And so in a sense, like in the end of my year, whenever it rains, it snows. It can rain and snow in the beginning of the year, but the reason for that is being different. At the end of the year, it's fully conditioned on the rain. So here are my results again, like one prediction for each day of the year. And you can see it's again picked up this pattern. At the end of the year, it's almost only, again with some statistical noise, raining and snowing. Whereas in the beginning of the year, it rains and sometimes rains and snows. And why? Well, because it does, and in fact, the beginning of the year is generally sometimes rain and snow. Now, you may not be convinced by this. Fortunately, we can look a bit into the model and see what it has learned. And we've heard this by Oliver, the excite techniques. You all know how they work. When building up this context, you look backwards at the previous tokens and assign an attention. And we know the model shouldn't pay much attention to rain in the beginning of the year, but much attention at the end of the year. And actually, if you look into this attention head, you can see that there are some specialized ones that have picked up this pattern. In case you wonder why it sometimes says rain and snow early, there it's conditioned on a cold system being there. So they really pick up intricate patterns even in the small case. And here come to my last slide. I've been being rushed. So yes, I think this is a proof of concept that transformer-based large language models can indeed be made time-aware by simply adding a temporal dimension to the token embedding. All kinds of fascinating implications for an application. I don't read them to you here. There are potential next steps that I could investigate. I like the second one a lot because there is information in this temporal dimension. It could actually make training more efficient because it helps the model to decipher patterns that are in there, which it otherwise needs to decipher from the implicit clues. I didn't do this, partially for lack of time, but basically I think because that point, like, as fascinating as the idea is, I see challenges towards an application. Now, this is a different architecture, so you cannot simply use an existing model and fine-tune it. We could by saying like, okay, this model is like for today, and I add onto it. But basically, I think this allows to training from scratch, and we don't have to compute to do this for any serious case above the one that I've presented. Also, it loses the charm of metadata-free self-supervised learning. Plunging is into the murky depths of data curation. Now, we would have to give each token sequence a date, and we have a lot of historians among us. That's not so easy. All kinds of questions. You know, you have to do this, and then there's a question. There's a reprint. When was that originally uttered, and so on and so forth. Last remark, being here, I realized that I always thought of like a generative, like a decoder, a causal mask. Maybe there is a use case in building just an embedding model, just some bird-like embedder based on the same principle for a targeted thing. So it doesn't have to learn all the intricate patterns, but only the ones that are relevant for the task that you put it to. And if someone has an idea, I'm happy to do it or ask me for cooperation. Yeah.
Thank you, Jochen. Thank you for the presentation. Oh, many questions. Maybe I point at you and then we follow the sequence with questions, and maybe you try to shortly answer, briefly answer 1, 2, 3, 4, 5. 1. You're 1.
Thank you for this. One application I can already think about for our own project that would be very interesting. Can you use this, as you mentioned at the end there, with embedding models? Can you use it to model semantic shift over time, right? So, for example, for our project, we have text over 200 years. Could we somehow put a token in the embeddings model there, so it gives us, every 10 years, it can give us, some sort of relationship to this semantic meaning over time? That would actually be an extremely helpful application of what you're talking about for our project, just as an idea.
I was answered to answer briefly. The answer is yes, of course you could do that.
2.
Thank you for beautiful talk. I can also elaborate because I did quite the same approach, and I basically extended facts also with identifier. So what you do is just basically creating facts, and put in timestamp. But also if you let persistent identifier to be able to track the source from where it's coming. So I did this on spreadsheets just to ask on specific data points. So I'm basically asking what was GDP per capita in Germany according to this source, and it's bringing me specific value. So if you'll do the same, it will be like really fair infrastructure in the end.
Yes, it's. I had this on my last slide, and I had to skip it, and I'm happy to discuss this further over the break.
Yeah. Thank you. 3.
Yes, that's me. Of course, great idea, awesome idea. It's just, unfortunately, of course, it has already been done. There are several papers that have done this. Even Nina, who was here yesterday for the first day for her thing, she has done it in 2019, and other people have done it. There's this literature on semantic change detection through LLMs, and these things are called time-aware LLMs. There's also TempoBird and all of these things. Probably have looked into
it. Is there a
this.
generative model? That's my question there.
If it's a generative
I mean, of course, to put it into embedding of a super modest encoder, that I can see. But, you know, something that can really, the way we think about GPT, like you can have an instruction thing that you can talk.
I'm not sure if I just know that there are lots of papers who did this with encoders.
I'm happy.
So then
happy for reference.
No discussion, no, 4. My numbers, somewhere I pointed 4, I have 5, 6, and 7. No, okay. 4, 5, 6, and then it's closed. You are 7.
Thank you. I'm 4, I think.
You're 4, yes.
Another attempt at suggesting literature that might be of interest to you. There's a paper from February of this year called Temporal Heads, something like that. And they have discovered attention heads in large language or foundational models and in multiple models where they have somehow, where they organize their temporal awareness, and this can be triggered by key sentences and so on. So that's not really, it's not really clear that this really is easily operationalizable. But at least we have instruments to work or to identify how large language and generative large language models organize this knowledge.
Thank you for this comment.
I think I can think of one way I can maybe have an idea of to solve one of your challenges is one of the challenges you listed is that it may be unscalable because you have to completely change the architecture, right? You're instead of 512 embedding size, you have to take one of them and dedicate it towards time, right? If you were to keep the same architecture but change the modeling task, so instead of doing next spam prediction or next word prediction, maybe you mask the time that's in the text, or you have it date the text at which it comes from, because you could have an imagine where you have text data and you have multiple dates, and the model, the objective of the training task is to determine what date that document originates from, right? If you were to change that, then you can actually use the same data, right? Because you don't need additional data of what time it is, because you can detect from the text itself, and you can use any of the original vanilla architecture. It's the same embedding size, but now your training task is different. That could help you train an encoder model, which people have suggested there's already been encoder models for this, but then you can tack on a decoder head. So you have an encoder-decoder architecture where the information is encoded in the encoder space, but then you have a decoder, and then you can benchmark that against your decoder to see which one is better.
Sounds reasonable. Just quick remark. It may, from the now speaking from the point of the historian, that may deteriorate this method in terms of the assignment of the date. The further you go back in time, probably work better for more recent documents. But that's just a small remark.
Okay. First, I thought exactly right. That's what we have to do. But then I had second thoughts. Time is somehow not only an intermediary, right? It rains and snow because the sun is like this, the earth is like this, and so on. So is it really necessary to have time explicitly in? Because it should all be there in all the other factors, right? It's only an intermediary at the end, a proxy or a...
Again, I said, this is what I said in the beginning. Clearly it is there, and they do develop an understanding. But if you look at it, purely from the point that I've tried to allude to, how it works, it's built up at pains because you have these contradictory things that you only resolve through these very intermediate steps by saying, but for the long short-term memories, there's also a remark that appeals to that being earlier because it's then said that it was in the past. It is there, but why not? In a sense, it's quality in, quality out. If we have this data and we know that dimension carries a lot of information, and if there's a meaningful way to put it in, we just help the model, and we can assume it gets better, or at least more efficient in training and picking up the patterns that we wanted to pick up.
Thank you for your presentation. Very highlighting and interesting. And it highlights me something about time. It can be circling or it can be linear, and you're dealing with more of a cycling time there with seasons or with the day and the morning or in the afternoon. Would you need two tokens or a different way of dealing with the linear time with the decades or the years and stuff like that, comparing to cycling time?
Of course, I mean, you gave the answer yourself. I thought about this with the years. I just didn't have the time to do it. You would have to reserve 2 dimensions, do it cyclical sine, cosine. And then again, if you really wanted to do this, one should invest. Thought is like, maybe you can reserve more dimensions because there are different aspects of time, one that codes more for the long coarse-grained developments that happen on long time scale and more finer. What the best design is there based on that basic idea is totally open and needs some reflection, I'd say.